Good morning, everybody, and welcome to Astronomy 100. Today is August 30th. We have quite a few things to cover today, so I'm hoping that you guys are following. A lot of you are not live for one reason or the other, and hopefully you guys are watching the recording. As I said before the recording started, one assignment has been graded. If you have questions about it, I'd be more than happy to discuss them in private. However, if you did not receive the full credit for the assignment, there is actually a comment that I put in there. Please go through those comments. They are very important. They help you basically do the next assignment better, so that to fix whatever needs to be fixed. So I encourage you strongly to read through those comments and make sure you understand them. If you don't, please let me know. I'd be more than happy to schedule a private session during or outside of the office hours. And I also plan to be on campus tomorrow. So if you guys are interested to actually meet in person, I will be most of the morning in there, if not until like 1 or 2 p.m. I'll be in campus. And my office number now is known, so actually I should probably send a communication to that. And it's in the 2700 building, and it's office number, what is it, 777? So it's an easy number to remember. Okay, it's 3 sevens. So it's in the second floor with the offices of the faculty, and it's right there. So just when you come in, go around the goes around, and you go when you go around, you will see it. So again, we're continuing. We have quite a few things that have been posted on your canvas. So I'm hoping that you guys are following these steps, because exams are around the corner. And actually this week has 2 assignments in it. One of them is a quiz and the other one is a homework assignment. So things start to pile up if we really don't take care of business in a sequential fashion. So let me share with you guys the screen to see what I'm talking about here. Again, this week we have the review from the previous week. The previous week dealt with some key concepts that hopefully you guys have had the chance to go through thoroughly. Every week there are several units. In the first 2 weeks there are 3 units each. This week has actually 4 units. What that means is you guys need to open the book. The book does not call them chapters, they call them units. The book is divided into parts, and each part has units in it. So this week we have 4 units. They're kind of light compared to chapters, so that's why they don't call them chapters. They are actually more like sections of a chapter. So that's why I put them together in here. Each unit is about 3, 4, 5 pages, so it's not really heavy in reading. The first 2 potentially could be about 15 pages. Now we're talking about almost 20 pages or less so of the book. So this is the level of reading that you're expected to do. Now, you may read a whole unit and still is not clear for you. What the purpose of this PowerPoints in here is give you the nutshell, basically the summary of the unit, what the main points of it is. I still go in person and talk about those reviews for those units. And I do it before and after so that we have a clear understanding of what needs to be done. Now, granted, what I say or what in the PowerPoints is not everything. So comes a quiz time or an exam time, you may see things that are, if you wish, buried inside those summaries. So you really need to dig through them. That's why reading is important. Okay, going through those units is very important, because these quizzes and the exams, they don't just go through what we talk about in terms of summaries. They talk about everything. So you have to have a full understanding of these things. So what came out of the first 2 weeks is the following. main thing in here is the MKSA system. As a matter of fact, let me delve straight into the quiz in here and talk about it. Okay. This is worth 36 points. I am logged in as a student, as a test student. This is not a real student, okay? As a test student. You have exactly half an hour to complete the task. So there are 12 questions. You have about 2.5 minutes per question. Okay, that's the average. Some questions probably require a little bit more time. Others may just basically go through them and you know exactly the answer to it. So you don't really need to spend that much time. Here is the deal. After you complete the first task, you cannot take, the first attempt, after you finish the first attempt and you submit, you cannot right away start the next attempt because you'll have 3 attempts at this one. Okay. You have 3 attempts at it. Okay. I did not specifically say that in here, but there are 3 attempts. Okay. So the system will take the highest score of the 3 attempts. If you're not satisfied with your first attempt, or even if you are satisfied with your first attempt and you would want to take the second attempt, because there is no penalty in it. So even if you do less in the second attempt, it's not going to take the last one, is going to take the highest. It's not going to average them either. So there is no harm in taking the second and the third attempt. But before you do that, there is a delay. You cannot take it immediately. The reason why I'm doing that is so that to give you a chance to go through the units again. These are the first week's units, the 3 of them. You need to read them thoroughly, make sure you understand them. You cannot rely on the fact that the questions, now you remember them, maybe the second attempt you will have a better guess at them. That's not going to work because the questions, they change. So you really truly have to have an understanding of what those units are talking about to make sure you do the best that you can in this quiz. So again, since it's a freebie, basically 3 chances. If you don't score the 100% score in it, just take it a third time, just to make sure that maybe the third time will be the best, okay? After that, that's it. Those are the 3 attempts that you're allowed into this one. It has a due date, which is on the 11th of September at 11 p.m. where you're going to submit this final quiz. So it's an important one, and you will have some of them throughout the semester. This is one of them. Okay, this is one of the occasions, the key concepts. There will be few more down the road. So in addition to homework type assignments, which brings me the other type of assignment that you have in this week, which is this assignment. This is a homework. It does not have a time limit onto how much you can complete it in. You can take half an hour to take it, you can finish it, or you take an hour to finish it. It doesn't matter. You take half a day if you want to. The key thing I want you to encourage you to do is work in teams. Okay, you are strongly urged to work in teams in here. Please make sure the team is around at most 3 to 4 people. Don't make a very large team. That is not something that I would want to see. You have to include everybody who worked on you in that assignment. Again, the purpose of this type of assignment is for you to understand it. Okay. Of course, if you don't submit it, or if you submit it wrong, or if you don't understand what's going on, you lose points. So this is a graded assignment, okay? Make sure you do it and you do it right. If it's still not clear to you, please ask me, okay? The purpose of a homework assignment is not an exam, is not to test your knowledge, is to help you know what needs to be known, okay? So that is really the idea behind it. So you can research, you can look at the book, you have plenty of time to take care of this one. This one also has a deadline, which is the 11th of September by 11 p.m., which is the same time when the quiz is also due. So make sure you do both of them and you take care of this. Now, use complete sentences. You cannot use short answers. Let's say, for example, the question is asking you at some point, I don't know, to have 30 divided by 40. Do not put the answer to be 0.75. What is it? Yeah, around that number, whatever. Okay, I think that's how the answer is. Okay, 3 divided by 4. Yeah, 3/4. That's 0.75. Don't say put the answer just like that, 0.75 or 75%. Or you need full sentences. You need a verb. You need description. You need to be explicit. Part of the purpose of this one is to help you able to communicate your ideas, and that's what we're looking for in here too. So the question was asking you for something specific. This questions, by the way, deal with the seasons, with the tilt of the axis of the Earth. So you have to be verbose. You have to explain what the answers are. Okay. So those two problems from page 50, and that's for both editions. So that's what I looked at. They are exactly verbatim the same questions, and they are for both editions the same one. So it doesn't matter if you have the 5th or the 6th edition, it's the same problems. Once you come up with an answer, you have options. So let me start the assignment. I'm a student, okay? I'm starting the assignment. What can I do in here? I have several options. Either I upload a file or use the webcam camera to basically describe what the answers are, okay? Or write the comment in here or do to the text answer. So instead of doing the comments, and I know I made sure I ask you, you can use even the comments if you want. Instead, I can use the text in here. It's more of a rich text environment. I can bold stuff, I can underline things. I can do a lot of things in here. I can click on this ellipses, and one of the things I can write in here is a math equation. Okay, I don't know if the pop-up shows in there or not. I can write 2/3, for example, and what is this? Switch to basic. Can write a fraction, for example. It's called a fraction. Two over 3, and look at it. I can insert it from here. So I can do a lot of things with this one, and here it comes up at 2/3. So in other words, this is far richer than having to struggle with the plain text in here. If I want to do 2/3, probably that's the best I can do in here, okay? So in other words, you have different ways of submitting your assignment. You have plenty of methods of submitting your assignment, but do it before the deadline, the 11th of September by 11 p.m., okay? A text entry box or a file upload. You have the options. Do whatever you want to, as long as you tell me at some point, I worked with so-and-so from the class. You can include his or her name, 1 or 2 more people with you, okay? So that is important because I want to compare your work to theirs. You don't have to agree with them. If they don't agree with you because you think you are right, state the fact that this is why I think this is correct, okay? But it's a good idea to work with other people to try to establish communications and rapport, try to convince them, they convince you, and at the end you come up with a consensus. And if not, hey, you stick to your what you think is correct, okay? So that is the idea in here. I'm not going to submit this one because this is not for your students and it's going to come up with a mess down the road. So I'm going to go back home in here, leave. So the live discussion is going to go here. Today's question is basically related to all of these things. And the units are here. Okay, one of you guys is submitting. So we'll talk about these units, okay, because they are important. One of the things that we talked about last week, and it's going to be heavily tested in here and asked in here also, is, or at least last week, is the issue of coordinates, okay, how we locate objects in the celestial sphere. And I want you to make sure you read all of these units and have full understanding of what they are, because they are important. On Earth, because it's a sphere, the things we use are the longitude, okay, it's measured in degrees, or the latitude, and it's also measured in degrees. So you have the equator on the Earth, And from the equator to the North Pole, it's 90 degrees. And from the equator to the South Pole, it's another 90 degrees, but in the opposite direction. Okay. So you have full 180 degrees from go to pole. Whereas you go full circle in here, it's 360 degrees from east back to east when you go counterclockwise. But usually in the measurements, they go actually clockwise in this case, which is in the negative direction when they are doing the measurements. But that's fine. Okay. So you go east, south, west, and then come back to north. And then from north, you come back to east. And that is a full circle of 360 degrees. So those are the altitude and the longitude, or the longitude and altitude in this order. Okay. East, west is longitude, north, south is latitude. Okay. Then we also we take this, the equator on the Earth, in the sky, and now we have the celestial equator, which is a projection of the Earth equator on the celestial sphere. What you see above you, the dome, basically, or the entire sphere, that is a projection of the Earth around everything. Okay. Then in this case, we don't use a latitude anymore, but we use the declination. Okay, we go the declination from the celestial equator all the way to Polaris, basically to the North Pole, which is a projection of the North Pole on the sky, which is Polaris. Okay, and again from 0 to 90 degrees north, and from 0 to -90 degrees south. Okay, so that is a description on the celestial sphere. So we have the declination. Instead of using the longitude on the Earth, we use a projection of that in the celestial sphere, and that's called the right ascension. Okay, and the right ascension actually goes again clockwise. Okay, and does not use the degrees; it uses just the hours, and it's similar in a sense. If you go full circle, you would go 360 degrees on the longitude, but on celestial sphere you go 24 hours. Okay, so that is in a sense how these measurements are. And it's very important you have an understanding of how the geometry is used in space. So that is actually part of the stuff that is described in detail in the book. Okay. So if you have any questions about this, on how to locate yourself, because we are in a latitude of what, 38 degrees, okay, and or 34, 35 degrees. So that means Polaris is actually, with respect to the horizon, sits about 34, 35 degrees for us in here. So if you go tomorrow and tonight, I should say, and look at the north, where is my north? This way north? Yeah, this way. Okay. This is the north. Okay. So if you look from the horizon and you raise your finger and you follow where Polaris is, you will see that it is about the position of about 30, 35 degrees from the horizon. Another thing also that the book uses extensively is some sort of an order of magnitude of the angles, because a lot of times you will find yourself finding angles, and most of the time you don't have the proper ways of finding the angles. So what you do in this case, you can use your index or whatever, your thumb. Thumb is slightly bigger than the index, and this would be about probably 1 degree in the sky. Okay, if you take 3 of them, that's about 5 degrees in the sky. Okay, if you put your from end to end, you're looking to about 5 degrees basically in the sky. So that's how you locate objects, how much to move in the sky. Now, if you open this, the two sides of the fingers, then in this case you're looking at 10 degrees. No, is it 10 or yeah, 10? I'm trying to remember. And from here to here, it's about 25 degrees. Okay. So again, go through those conventions in there. Most of the times, honestly, I don't use them. I have on the app in there, I have the measurements for it. Okay, that should give you an idea, rough idea. Okay, so that's basically some of the things that you can use in the to find the objects in the sky. Again, so those are some of the stuff that you should have covered in all of these units, which brings me to a very, very important point in here. Reading is essential. Reading is exactly what you're going to be graded on. Units this week. We have 4 units this week, unlike the previous 2 weeks where we had 3. Okay, so we have 4 units of reading in this week. So you have to have the book and open the book and go through all of these units and read them. We have unit 8, 9, 10, and 11. And I'm going to talk briefly about what these units are covering so that we have that, in addition to a summary that will come next week, and in addition to this PowerPoints in here, and that all of these things do not replace your reading. Your reading is still required, okay? The reading is still a must in here, so you have to have that. So, Unit 8. Let me find it first. And let me stop sharing. And let me share Unit 8. So Unit 8 deals with the lunar cycle, the cycle of the moon. The moon goes around the Earth in almost 1 month. Okay, as a matter of fact, the word month is borrowed from the word moon, because the moon goes around the Earth in almost 30 days. That's exactly 29.5 days to go around the sun, around the Earth, I'm sorry. Okay, and it's in its rotation around the Earth. In doing so, it goes through several phases. Okay, and that's what you're going to be discovering in this chapter. Okay, the different phases from when it's born, when it's basically when it starts to appear, and then until when it becomes a full moon. Before that, it's going to be quarter moon, increasing in size, so it's waxing, and then it's going to decrease back from a full moon down to a quarter moon. Before that, it's going to be a crescent, and then it's going to be, it's going to be a crescent at some point. So again, it's going to be either increasing in size or a decreasing in size. So that's a full cycle basically of the moon that you're going to look at it. You need to really know the position of the moon and the Earth and the sun with respect to each other on the entire cycle. There is an assignment that is going to come in here. That is a required assignment that you need to complete by doing observation, lunar observation for a whole cycle, for a whole month, basically. You're going to be going out, looking at the moon, and if the night is not clear, you have to wait for the next night, okay? If there is clouds on that night or something, then you have to wait for the next night. Try to do the observation the night before and the night when it's recorded on the assignment, and the night after to have a better accurate reading. And just in case, if it's cloudy the night before, hopefully you will hit it on the nail on the day when it's required. And if it's not, it's still cloudy on that day, hopefully you will still hit it on the day after. So we will have data no matter what, okay? So that is basically the observation that you're going to be doing. You need to know the different phases. You need to know actually there is actually a big distinction between the sidereal and the actual cycle. And that is because the actual cycle itself is related to the position with respect to the background stars versus the fact that the Earth is moving around the sun, so there is a shift in here in the day. So the actual cycle is 27.3, but it appears to be 29.5, okay? So there are all kinds of information in here. One of the things that I want you to really pay attention to is for the lunar eclipses, okay? How many and how often? And solar eclipses also, and why, okay? The reason is because the Earth goes around the sun on a plane like all of the other planets. We'll talk about why that is. It has to do with something called the conservation of the angular momentum. The angular momentum, because it's a conserved quantity, all of the planets ended up on the same plane, more or less, slightly more or less depending, and that's because of the perturbations coming from after the solar system was formed. So you have the planets on the plane. We call this the ecliptic plane, okay? The moon, when it goes around the Earth, is not on the same plane. It's not on the ecliptic plane. It's slightly tilted with respect to the ecliptic plane. So that's why sometimes the moon is just between the Earth and the sun, but there is no solar eclipse, or there is no lunar eclipse. We don't see any of that. So you don't see that because the moon is above the plane or below the plane. In either case, its shadow is not falling on the Earth, or the Earth's shadow is not falling on the moon. That is because of this tilt. The moon, think of it this way, the Earth is on this plane and the moon is on a different plane, And now it's above or below, so it doesn't matter, okay? However, when the two planes meet, cross each other, then that is when you will have a solar eclipse, meaning the moon is hiding the sun, or the lunar eclipse, meaning the shadow of the earth hides the moon disappears for a few moments, okay? That is because the plane where the moon is spinning around the earth and the plane where the earth is going around the sun, they cross each other. During those times, you will have lunar and solar eclipses. These are key concepts from this unit. You really have to go through this one, and hopefully you have a full understanding of what these units are. Okay, let me stop sharing to go to the next units, because this is not intended to be a replacement of the reading or even a full description of the chapter or the unit, but just basically a summary of it so that we will have the main ideas. Let me go to the next one, which is calendar. Again, because of the fact that the moon takes about 30 days to go once around the Earth, and the Earth goes one full year to go back and come back to its initial position. That is basically what we know today. In the old days, they what thought the sun also was going the Earth in 12 times as much as the moon goes once around the Earth. So the moon goes once around the Earth from going from when it's born back to when it's born again. That's about 30 days. and the sun appears to come back to the same position in the sky also, because it's again, it changes positions every 360 some odd days. So if you do the math, you will find it's about 12 times, okay? 12 times if you make corrections for those days. So the year was divided into 12. And the week was divided into 7 days. Why the week 7 days? Because of the fact that if I look at the sky, there are the moon, which seems to be going around the Earth, one. Then there is Mars, which seems to go around the Earth again, also in a periodic fashion. The background stars, they seem to be sitting still. So, and then after Mars, there is also Mercury that seems to also be doing the thing. As a matter of fact, it goes next to the sun. As the sun goes around the Earth, the Mercury goes with it. And Venus also comes with it also later on. But I'm trying to put them in order. After Mercury, we also saw Jupiter also going around the Earth too. And then Venus, and then Saturn, and of course the sun. So we divided the week into 7 days, according to all of these objects in here. The moon and the sun. So we have Sunday and Monday, the day of sun and the day of the moon, followed by the day of Mars, which is Tuesday, followed by the day of Mercury, which is Wednesday, followed by the day of Jupiter, which is Thursday, followed by the day of Venus, which is Friday, and finally the day of Saturn or Saturday, okay? So those are how we divided the week into 7 days, because of the fact that we have 7 celestial 5 planets that we know of, and the moon and the sun, okay? So we have 7 days because of that. So Monday is the moon of the moon. Tuesday is the moon of the day of Mars. Wednesday is the day of Mercury. Thursday is the day of Jupiter. Friday is the day of Venus, and finally Saturday is the day of Saturn, and the day of Sunday, which is the day of the sun, which is Sunday. So those are how the weeks were. And it's a good thing we didn't know about Uranus and Neptune then, because those two also do the same thing. Those are 2 additional planets that we didn't know of at that time, okay? If we knew about them, then the day probably would have been 9 days. The week will have 9 days, I'm sorry. Wouldn't this be fun to have a 9-day week? You have more days to do your work. If you're working, okay, if not, more days to anyway. So that is basically how the week was divided into basically 7 days. It's based on this, and then later on because the lunar month actually and the lunar cycle is off by 11 days compared to the Gregorian to the solar year, if you wish, then we had to make corrections. That's why in the lunar month, and it's used actually in the Islamic religion, actually you will see it actually in the book and here, that the lunar month actually rotates, spins compared to with respect to the in other words, the day that happened this year, let's say for example this Monday, August 30th, it's going to be off next year by 11 days and so on and so forth. That's the difference between the two. But again, even the word month in the solar month is actually borrowed from the rotation of the moon. And it's the influence of this, especially when the three religions, Judaism, Christianity, and Islam, took those divided the year this way. It has tremendous implications for even modern day culture. As a matter of fact, for non-religious cultures also it had that influence. So astronomy had a lot of influence on how to do time, and also agriculture. When are you going to plant those crops? When are you going to, plant those seeds? When are you going to get? So you need to know the season. So that's why astronomy was important here. So again, please go through it. In addition to that, you have the leap year and why we have to make correction, because actually the Earth, as it goes around the sun, it's not exactly 365 days. So you really have to make that correction every 40 years for it, for February 29th versus February 28th. So again, that is something that you're supposed to be reading in here. And again, you're going to be tested on these things down the road. So I expect you guys to do the reading. This is not in lieu of reading the chapter. So this PowerPoint's in here, and my presentation or my summary of it is not replacement for that. Again, you're supposed to do the this ones, and if you have difficulty or if you have questions, please let me know.
Professor?
Yes.
Are these units going to be on the quiz as well?
Not this quiz. This is only from first week.
Oh, okay.
Quiz is first week only, but this one's down the road. You will be heavily tested on them. So please, okay. For the second week, you have the homework, and for the first week, you have the quiz. So each week is covered this week in terms of testing. Okay, so let me share with you. I don't know if I shared it or not. I did not. Share. So this is the third unit of this week that we're going to be talking about. And this one has to do with how amazing our ancients were. Our ancestors were in determining things that even today, apparently, we're struggling with, okay? They determined that the Earth is spherical a long, long time ago. They determined its radius, not only spherical, but how big it is. They determine how big the moon is in terms of its radius, how big it is. They determine the distance from the Earth to the moon. And they determine the distance from the Earth to the sun with amazing accuracy. And today, you still have people who still have phones and access to the internet and do YouTube who think that the Earth is not, somehow is flat. So let me give you briefly the argument that hopefully you will enjoy when you read this unit. First of all, when they noticed two phenomena, two simple examples. One of them is the following. As during the during a lunar eclipse, there is the shadow from the Earth to the moon. And that shadow appears to be curved in a circular shape. So that indicates that the Earth must be spherical in shape. That's their conclusion. If it was square, if it was something else, it could have different shape. If it was a flat disk, yes, it probably is going to have flat circle on this side, but if they are in a different position, the circle would look different. So if this is where the Earth is a flat, yes, right now it's giving you a circle, what looks like it's a circular shape, but if I turn it around, it should give me a line now. But that's not how it happens. So if you change your position, always giving you a circular projection, which means that what you are on is actually spherical shape. That's an important argument. That's a very good argument. Just by looking at the lunar eclipse. Of course, nowadays, people without any observations, they don't go outside and bother to look at the lunar eclipse. They have no idea what that is. And yet they go on YouTube and make all kinds of nonsense stuff in there. That's one thing. Okay. The other thing also that they noticed is if you go, for example, on a boat, and they used to sail a lot, you will see that as you leave the port starts to fall below the horizon little by little. So that means that you are curved. If you come back to it, it starts to rise from the horizon. That is actually the curvature is indication that no matter where you are on the Earth, in whichever direction you move, the horizon is actually going on a spherical shape, okay, until you come back to that point. So that was an indication that the Earth was spherical, and there's no question about it. It was a sphere, okay? Not only that, but in ancient Egypt, they were able to find the radius, how big that sphere is. It's amazing. During the time of the year, the southern Egypt will be the sun will be immediately above it, and that's typical, okay, for especially since you are not too far from the equator. At that point, there is no shadow. If you put a stick on the ground, it does not give you a shadow, zero shadow, because the sun is immediately above you, okay, during a certain time of the day. If you move on the same day to another city in Egypt, Alexandria, for example, there is a shadow. And if you compare the two shadows, that makes an 18-degree angle, whereas this has no shadow. So that means going from southern Egypt to northern Egypt takes about that curve. You're going on that curve. So if I know the angle, which is 18 degrees, and if I know the distance, they use the stadia in that time, how many stadiums you're going to put one next to one another to find that distance. You can project it for the whole sphere and find the circumference of the sphere. And they found the circumference of the sphere using simple math, which is just 360 degrees versus 18 degrees. That's all, for circular, versus that distance. Okay. And it's amazing because then you just divide by pi, which they know. Then you find the diameter of the Earth, divide that by 2, and you have the radius of the Earth. So we have a very good idea how big the Earth is. Not only we know it's a sphere, but we know its radius also. So during a lunar eclipse, what happened was how many shadows, or during a solar eclipse, how many shadows of the moon are cast on the Earth in here, or vice versa. You will see that there is a ratio of 3 to 1. Okay, that the Earth have 3 times appears to be bigger than the moon. So from here you have an index. So now you know the diameter of the Earth. Take that divided by 3, and you will have the diameter for the moon. So you know how big the moon is. Another thing that you could do also is take coin. It doesn't matter how big it is. At that time, they didn't have nickels, so they had a different coin. Okay, doesn't matter. As long as you can measure its distance. This is about 2 centimeters. Okay. This is about 2 centimeters. Take it and put it in front of your eye, very close. It will block everything, including the moon, by the way. And if you move it away, it starts, other things that were blocked starts to appear in it, especially the moon, for example. Move it back until you reach a point where it covers just the moon, not anything else, just the moon. If you push it any further, the moon starts to appear, the sides of the moon starts to appear. If you move it any closer, it's going to still cover the moon and more. You don't want that. You want just barely the moon. Then use simple ratio of distances, okay? Ratio of distances from basic geometry, the tangent of the angle, actually, to be more specific, to find the distance to the moon. Because you know how big the moon is, and you know how big your coin is. The ratio of these two is the same ratio as the distance from your eye to the coin and from your eye to the moon. It's amazing, 380,000 kilometers. So we know how far the moon is. See how much we know at that time? We know the Earth is spherical, we know its diameter, we know the diameter of the moon, and we know how far the moon is. Not only that, when the moon is a quarter moon, so here is the sun is on this side, we are on this side, and the moon is in here. So this, as it projects, where half the moon in here projects half of it, this is a right angle triangle. Since now you know the distance to the moon, and you can find the angle with which the sun is projecting itself. You find this angle using simple trick. You can find the hypotenuse of the right angle triangle. So you know how far the sun is. Please read this chapter, it's amazing. And all of those people who are talking about flat Earth things, they don't know this. These things have been resolved. They have been resolved thousands of years ago by humans who did not have access to nothing. They didn't have telescopes, they didn't have anything. All they did was simple geometry and observations. That's all. Simple geometry, that's all. It does not require complicated math or complicated telescopes or going on a plane and doing anything. It's amazing. So I hope that you will enjoy this unit. It's fascinating. And if you have any questions about it, please let me know, because that is actually going to be the point today, that reading the units is important. So tests and quizzes are based on understanding and reading the units in the book. That's what I want you to post really today, because it is very important. Does everybody see the unit, the discussion points of today? I want you guys to really take that into account. We're going to say something, Jesus? Good?
No, good.
Okay, very good. So this is important unit that hopefully you guys will enjoy. This is one of the things that is fascinating, and I want you guys to enjoy it. And if you have any questions about it, please do not hesitate to ask. The last unit of this week is Unit 11, and this one deals with the motion of the planets around the Earth. Okay, two key positions or three key positions for the planets around the Earth. First of all, are they in opposition on the other side other than the sun? Sun is on one side and they are on the other side, or they're in conjunction, meaning they are on the same side of the sun. That's one thing. In addition to two quadrature positions, which are in the opposite as they go around, in their apparent motion as they go around the Earth. Okay, so using this different positions, we notice that one of the planets, at least, now we know that all of them do, have actually what looks like what astronomers called a retrograde motion. In order to understand it, Ptolemy came up with a model, because Ptolemy believed that the Earth is the center of the solar system. And he said that as these planets are going around the Earth, and as everybody else is going around the Earth, some of these planets, especially Mars, seems to be going on its own circle around the circle that is going around the Earth. So there is a circle around the circle. This calculation turned out to be a little bit more complicated, so you really had to have a smaller circle in here. So this is the epicycle for it going around the circle. It came up with all kinds of geometry in here to explain it. This is the so-called geocentric model, where the Earth is the center of everything. This messed up things, because from Ptolemy's time to Copernicus was about 13 centuries. When by that time the calendar was a mess. Christmas was happening instead of December. Nowadays, December was happening in the spring, according to the calendar. The dates were a mess, so you cannot predict anything about any holiday. You don't know when anything is happening. So that's why Copernicus was asked to recalculate the calendar, fix the calendar. In doing so, he had to get rid of this geocentric model, and he had to come up with the heliocentric model. In the heliocentric model, the sun is actually the center of the solar system, not the Earth is. His mistake, if you wish, if call it a mistake, he had to retain this idea of circular paths. Okay, that everything is going in circles because they believe that the circles are perfect shapes in here. But nonetheless, this explains the retrograde motion beautifully also. So this one explains the retrograde motion because as it's going around the circle, sometimes it's going on this side, it appears going backward, and the other times it appears moving forward, for Mars, that is. This one also the same thing. As you go around the circle, there is an activity, by the way, that is going to come down the road for the retrograde motion in here. So you really have to understand this unit for that. So you look at Mars, it's in here. This is you on Earth as you're going around the sun. Remember, this Earth is closer to the sun than Mars is. So if you look at the Mars in this case, Mars looks to appear to be in this point in the sky. These are background stars in the constellations. That's what you see at night. Now, if you wait a little later and you look at Mars, Mars appears to have moved forward like everybody else in here. Okay. So there is no problem in here from this week to this week. If you wait another week, the Earth is overtaking Mars because it's moving faster. So you look at it and it looks straight out. Then instead of moving forward, continuing moving this one, it appears to have moved backward in the night sky compared to the background stars. Now, if you look at it again later on, because it's moving, appears to have moved backwards so much. Then if you look at it again, now it's going to, because you see the projection, now you're going back into the same circle in here. You're not continuing in this line. Otherwise, it's going to move backward all the time. So in this case, because you're in a deflection point in here, it appears to start to move back forward again. So this explains the retrograde motion, even in this, where the sun is the center of the solar system. Not only Mars that does it, all of the other planets too. I mean, for the inner planets, actually, they are moving faster than Earth, and they appear to be in the night sky also. Their projections are different in here, but they still give you retrograde motion for Venus and all of the other planets. Using these calculations, based on the time and how much they take from the conjunction to the quadrature, this is what he came up with for the distance and how far they are from the sun. AU is an astronomical unit that you need to remember from the quiz, by the way. The quiz talks about the AU, talks about the MKSA system, and talks about the Parsec and all of these units that you really need to be familiar with. See, the astronomical unit is the distance from the Earth to the sun, which is 150 million kilometers. As compared to that, Mercury, according to the modern day calculation, the actual distance is 0.39. This is what he came up with, 0.38. Which is very close from the correct answer. And he was right on the money for Venus. Exactly also for Mars, slightly more than 1.5, a time and a half, the distance from the Earth to the sun. And then for Jupiter, he was slightly off, but not by much. A little over 5.2 astronomical units. And then for Saturn, he was a little off, but not by much still. Slightly more than 9 astronomical units, or almost 9.2 versus 9.5. This is the correct answer. So his calculations were very close from this. And again, the path actually he used was circular paths, and later on we'll see how Mr. Kepler corrected those calculations, these things in here. So it's amazing stuff that what we learn from these things in here and how they are. Now, for the quiz, I forgot to mention something. In addition to the astronomical unit, also, you need to know the light year. The light year is the distance traveled by the light in 1 year, 365 days. Each day is 24 hours. Each hour is 60 minutes. Each minute is 60 seconds. And the light in each and every one of the seconds does almost 300,000 kilometers per second. So that is the light year. It's a lot of number. It's a big number. It's 9 billion kilometers, almost 10 billion kilometers. It's a lot of distance traveled. So that's a distance. And then you have the parsec. The parsec is also slightly more than 3 times the light year. That too also you need to know. That's also for the quiz. The quiz also talks about the MKSA system, the metric system. The metric system is the meter for the distance, kilogram for the mass, second for the time, and also ampere for the current. We hardly are going to be talking about current, so that's why most of the time we drop the A, but that's basically we talk about the MKS system. Now, any other system of units is not metric. You have to be aware of that. The imperial system, which is the foot and the law, the pound and all of these things, is not a metric system. It's not the standard that we're going to be using for most of the time. And also the CGS system, which is used by a lot of scientists. The CGS system is not also a metric system. The CGS system uses centimeter for distance, uses the gram for mass, not the kilogram, the gram, and uses second for time. And uses all kinds of other weird units that are not part of the common day metric system, like the dyne for the force, and they use also the erg for the magnetic field, and so on and so forth. So this is another system that is not of interest. So you'll be asked questions to say, is this a metric system proper unit or not? What you're looking for is one or more of these letters: M for mass, kg for kilogram, S for second, and A for ampere. If any of this combination appear, one or more, that's a metric system. Sometimes they use derived units, like for example, the Newton. Newton is actually part of the metric system, but it's not a fundamental unit. So when they ask you fundamental units, you're looking for this 4 only. So if they say Newton, that is not a fundamental unit. Newton, as a matter of fact, is a kilogram times a meter divided by second squared. So it's not, if you express it that way, that is actually in fundamental units. The same thing, and that is part of the units, by the way, from week 1, so that you have to cover. For example, the energy. The energy in the metric system, sometimes they use the letter J for joule. And that is fine, but it's not in the fundamental units. In fundamental units, it's a kilogram times a meter squared divided by second squared. So those are some of the terminologies that you need to be aware of that are relevant for you guys for this quizzes. And again, by reading these units. Remember, the discussion point today is test quizzes are based on understanding and reading the units in the book and not something else. Not from the summary that I have just basically outlined for this week, not from the PowerPoints that I'm submitting in here just to help you basically in your reading, but you still are supposed to do the reading. And if you have any questions, you're supposed to ask, and I will be more than happy to help you with that, okay? So there was actually an item that I wanted to share with you guys today, unless you guys have any question for me.
Professor, isn't it true that the Greeks, I believe it was the Greeks who used like this giant pole to like cast the shadow, and then that would determine like the time?
Yeah, that is actually a good activity. If we have lab, we will build actually a clock, okay? Using the, it's really a nice device. So yes, it was actually used in, actually in Alexandria, there is such a statues, and now even in Washington DC, they have them all kinds of those monuments to measure the time. Yes, you can do that, and so they had amazing discovery. They had really discovered a lot of things, and we are, we're lazy. We're just sitting in front of our screens, and we don't hardly do any observations. That's the unfortunate thing of the technology that we seem to be living in. Okay, let me share with you the screen, because I really want to share with you this activity, which is important. And this is actually from Unit 4, page, let me share the screen. Page 32 from the book, okay? It's only one question, because we really have to get this things mastered so that we know what to do, okay? So you really have to have the book before you, and we're looking at question number 11. And it says, if a proton were the size of a large apple, about 10 centimeters in diameter. So here is a proton. And you need to find what the size of the proton is. From the book, you should go into the appendix. If not, probably doesn't have this data in here. Okay. The proton is about a femtometer, which is 10 to the negative 15 meters. That's what a femtometer is. Tiny object. Okay. The atom, which is much, much bigger. So here is the nucleus, and here the radius. Let's take the hydrogen atom, for example. The hydrogen atom, the radius is about half an angstrom. And an angstrom is about 10 to the negative 10 meters. So this is okay. That's the size of the atom. Relatively speaking, this is much, much bigger than this one because 10 to the negative 10 is much bigger than 10 to the negative 15. Since this is one of the quiz questions, let's find the ratio in here. The ratio. How big is the atom compared to a proton? We do the ratio. When I do the ratio, I better have the same units. So I'm going to put the numbers in here. The atom is about 10 to the negative 10 meters divided by the size of the proton, which is about 10 to the negative 15 meters. I have the same units, so I don't worry about this one. So I cancel them. If I don't have the same units, I really have to convert. Okay. Since I have the units, I'm in good shape now. I'm going to do a ratio of 2 powers. So it's going to be the numerator, do not change its sign. So if it's negative, it stays negative. The denominator, I have to change its sign. Since it's negative, it becomes positive. That is how you divide fractions. I mean, you divide the powers. So when you have 10 to the power A and you divide it by 10 to the power B, this is the same thing as 10 to the power A minus B. So if A was positive, it stays positive. If A was negative, it stays negative. If B was positive, it becomes negative. If B was negative, it becomes positive. Whereas if I do the multiplication, again, all of this is explained in the units from week 1, actually. 10 to the power B. This will be 10 to the power A plus B. When I do the multiplications, I keep everything. So if this is negative, it stays negative. If this was positive, it stays positive. If this was negative, it stays negative. If this was positive, it stays positive. So this is how you do a multiplication. This is how you do division. So in this case, the ratio is a division. So I have to do the math in here. Negative 10 plus 15, that is 5. So the ratio is 10 to the power 5. In other words, 10 to the power 5 is 10 times 10 times 10 times 10 times 10 times 10, 5 times, which is 100,000. So the atom over a proton is about 100,000 times bigger. As we know, much, much larger. Okay. Now, the question is, now we're not using the atom, the proton as this proton, femtometer, but it's an apple. So if it's an apple, proton is an apple, and the apple has a size of 10 centimeters. 10 centimeters is 10 times a centimeter is 100th of a meter, or 10 to the negative 2 meters. When I do this multiplication, this is to the power 1. When I don't put a number in here, I assume that it's to the power 1. So this is the same thing as doing the multiplication, this rule now. 10 to the power A times 10 to the power B, which is just keep everything the way it is. So it's 1, did not change, plus this one, which is a negative 2, that's all. and this is 10 to the negative 1 meters. So I did not change the sign. I kept it the way it is. That's why it's negative in here. It's 10 to the negative 1 meters. So if that's the case, the atom will be this 100 times this much meters. So it's going to be 100 times the atom. Since the proton is this much size, the atom will be 100 times 10 to the negative 1. And 100 times again is 10 to the power 5 times 10 to the negative 1. Since I'm doing multiplications now, all I am supposed to do is 10 to the power 5. I did not change this one, plus the second one, I didn't change its sign. And 5 minus 1 is 4. 10 to the power 4 meters. Remember, there is 1,000 meters in a kilometer. So for me to convert from meters to kilometers, I have to divide by 1,000. So in order to find the atom now in kilometers, I have to do 10 to the power 4 meters. And there is 10 to the power 3 meters for a kilometer. Okay. Now the meter and the meter are gone in the conversion. 10 to the power 3 and 10 to the power 4, that is the same thing as 10 to the power 3 minus, 10 to the power 4 minus 3. So I don't change this sign, and I change this sign now. So this is going to be 10 kilometers. 10 kilometers is about 6 miles. So if the proton was in the nucleus, which is the size of the proton actually for the hydrogen atom, was an apple, the electron will be 6 miles away from it. That's an important model to look at. If we do the distance to the Earth to the sun, if the Earth was an apple, if the Earth was an apple, or let's put the sun in the center, because the sun is the one, because the Earth plays the role of the electron. Let's put the sun. If the sun was an apple, how far the Earth is. So again, here is my apple. For the electron, for the atom, it's about 10 kilometers, 6 miles away. So this is the electron, this is the proton, okay? Now this is the sun now in our model, okay? The sun is 700,000 kilometers in radius. We multiply it by 2, it's going to be slightly over 1 million. So it's about 1 million kilometers, about, okay? And to be more specific, it's 140 or 1.4 million, okay? The Earth to the sun is 150 million kilometers, okay? So if I find the ratio again, ratio of the distance Earth-Sun over the sun, it's going to be 150 million divided by 1.4 million. This is zeros cancel, the same thing as before. And it will be left with 1,500 divided by 14, which is roughly 100,000. Okay. So I do the same thing. If the sun is in here, the Earth will be roughly around here, about 6 miles away still. So the size of the atom versus the proton, the nucleus, is the same size as the Earth versus the sun versus the solar system, how far the Earth is from the sun. So since there is empty space in here, that's the same thing. So the atom and the solar system are similar in this sense only, in the sense of size. That's all. Nothing else. Do not push this analogy further. So this is from the book. I hope that you guys look at this questions again. This is from Unit 4. Unit 5 is a little bit more complicated in terms of examples. So we'll see how we're going to handle that in terms of assignment. This is from last week's assignments, okay, from last week's discussion. So Unit 6, actually, that's where the homework assignment is. That's where you're supposed to work out those two questions on your own, okay? 12 and 13. Sounds good?
Yes.
Okay, very good. For those who came in late, I know we started a little early, so you can watch the first half. I think the point of the discussion today is reading is important. That is where your tests and questions are going to be based on the assignments, based on reading and understanding those readings. Make sense?
Mhm.
Okay, so I'm going to stop the recording.